Okay, so good afternoon, everyone. My name is Martin. I'm a tech lead in the reachability group at Socket. Socket is a supply chain security company, so we basically work with all aspects of securing third-party dependencies, including NPM packages. Before joining Socket, I did a PhD in static analysis and software maintenance of applications using NPM. Today, I am going to talk about vulnerabilities, and specifically talk about vulnerabilities in dependencies. So these are the kinds of vulnerabilities you will see when you run a command like npm install, and then toward the end you get this summary telling you that you have some vulnerabilities that you need to address. So the extent to which you care about these vulnerabilities probably depends a little bit upon the project you're working on. But if you're working for like a larger organization, there is a pretty high probability that that organization is going to have an application security team that will tell you to fix at least some of these vulnerabilities. But fixing vulnerabilities is something that we want to try to minimize because it usually involves upgrading dependencies, and upgrading dependencies is likely to break stuff. But I have some bad news. If we look at the number of vulnerabilities disclosed every year, it's just been growing rapidly. So we now see almost 3 times as many vulnerabilities as we saw a decade ago. And actually, there are some indicators that this is going to be even worse in the future because we now have all of the AI agents that are able to more or less automatically find vulnerabilities. But the good news is that if we take a typical software project and we look at all of the CVEs, all of the vulnerabilities affecting that project, we typically find that the vast majority of vulnerabilities are actually completely irrelevant in the context of that project. And let me illustrate why with a recent example. So this is a vulnerability that was, or the description of a vulnerability that was disclosed in the NPM ecosystem recently, affecting a package called system information. What we can see here is that it's a high severity vulnerability, so at least on paper, it's pretty bad. But what's really interesting here is that there's like this long list of conditions or prerequisites that must be satisfied for it to be relevant. And as you can see among this list of conditions, there is the fact that an attacker must be able to create files on the file system in any directory indexed by update DB. So I would make the argument that if an attacker can do that, you probably have bigger issues than this particular vulnerability. But what I want to focus on here is this condition up here that says that the vulnerability is actually only affecting the versions function from system information. And the reason why that's interesting is if we try to load in system information, we find that it actually exports 60 different functions, and versions is just one of them. So most likely, most of the people who use system information don't actually call versions. They probably depend upon system information for one of the other 60 functions. So what we would like is to envision or develop a tool that can help us automatically determine if we're using the vulnerable functions or the set of vulnerable functions from a particular package. So let's try to imagine such a tool. So a first naive attempt might be to do something like this. So basically use grep to find all the files that contain both the string system information as well as something that resembles a call to versions. But this has some issues, and one of the more severe issues is illustrated by the figure here at the bottom. So it's often the case that vulnerabilities are not in direct dependencies, but actually intransitive dependencies. And you can have a scenario like this, where the application, in this case, depends on Dartmind, and Dartmind is actually calling into the vulnerable part of system information, so it's calling versions. But the application is not using the part of DartMind that calls into versions. So in this case, the grep approach would tell us that system information, or the vulnerable part of system information is in use, when in reality it's completely safe to ignore this vulnerability because it would never be called at runtime. So what we need is a stronger approach. And the approach that I've been working with for many years now is based on call graphs. So the idea behind a call graph is to build a model of your program where you have a node for every function. So the nodes are represented by the circles in the figure on the right. And you have an edge for every function call represented by the arrows on the right. And what you can derive from the call graph is which functions call which other functions. So we can see here that, for example, summarize is calling process users directly, but it's also indirectly calling capitalize through process users and greet. So this is a call graph generated for this little toy program here on the left. If we can generate call graphs, we can basically take all of the functions in the application code, and then we can check which functions in the dependencies are reachable from the functions in the application code. And if there is a vulnerability in a function that's not reachable, then we know that that vulnerability is completely safe to ignore. So call graphs can become pretty big. This is a call graph generated for the system information package. Contains about 1,000 different functions and 1,500 edges between them. And you can imagine that if you have like a big application with thousands of dependencies, the call graphs become just even bigger. There are many ways to generate call graphs, but the way that we've been doing it is using this pretty old algorithm based on subset constraints, where the idea is it's basically a static analysis. So we go through all of the files in the application as well as the dependencies. Then we build a set of constraints. We have a constraint solver. And that runs for some time. And once it finds a solution, we can generate a call graph from that. And then we can conduct a reachability analysis based on that. So this is a lightning talk, so I don't have time to go into sort of details about how exactly the algorithm works. But there is an open source implementation available called Jelly, which you can find on GitHub. This is the tool I used to generate the call graphs you saw on the previous slides. There's also an npm package you can install if you want to try to run it on your own project. If you want to learn more, you can come talk to me at the Socket booth or reach out to me through LinkedIn or email. All right, thank you.